Welcome everyone to our video on determining the molecular formula of a compound. Before we get into this video, a few pieces of prior learning that you'll need. First, you should be familiar with mass to mole calculations. You should be able to determine the percent composition of a compound. And you should have already watched the video on determining the empirical formula of a compound. This video will essentially be a video tutorial where I go through two examples in how to determine the molecular formula from different pieces of initial information. The molecular formula is the actual whole number ratio of atoms in a molecule. And remember that the molecular formula, or MF, is always going to be a whole number multiple of the simplest formula. So remember our examples. We had compounds like ethine, C2H2, and benzene, C6H6. Both had different molecular formulas, but the same empirical formula. Ethine, a two-time multiple of the empirical formula. Benzene, a six-time multiple. And this fact is going to be key for us in determining the molecular formula. The first piece of information needed to determine the molecular formula of a compound is either the percent composition or percent by mass of all of the elements in that compound, or the empirical formula. Now, these are similar because, as you may recall, we used percent composition to find the empirical formula. So really, we're always starting with percent composition. And we can either find the empirical formula first and then find the molecular formula, or we'll have a shortcut way, if you will, to determine the molecular formula directly from percent composition. Regardless of which way we find the molecular formula, we need to know the molecular mass of the compound or the molar mass. Now recall, the molecular mass of a compound expressed in atomic mass units is the same numerical value as the molar mass of the compound expressed in grams. So you'll see these terms used interchangeably, and that's because they use the same numerical value. Now, even though we won't get into detail about this, I think it's important to mention where this information comes from. And these measurements, percent composition and the molecular mass, are fairly straightforward pieces of information to determine experimentally. In a high school lab, we're able to determine the percent composition experimentally through gravimetric analysis. The molecular mass of a compound is found using a mass spectrometer. So you recall back in atomic theory, we talked about the mass spectrometer used to determine the relative abundance and the percentages of each isotope for an element. Well, in a similar way, the mass spectrometer can be used to determine the molecular mass of a compound. So both of these pieces of information are information that you would determine experimentally. And it's easy to forget that when we kind of get bogged down in just solving these on paper and doing the mathematical problem solving. Let's switch over to the whiteboard now and get into the first example. In our first example, we're going to see how we find the molecular formula directly from the empirical formula. Here we have a compound which has an empirical formula of CH2O, so a 1 to 2 to 1 ratio of carbon, hydrogen to oxygen. As we just saw, the molecular formula will always be at some multiple of the empirical formula. In order to find what that multiple is, we are going to compare the molecular masses or the molar masses. So the molar mass of this compound is 120 grams per mole. I'm going to find the molar mass now of the empirical formula. The molar mass of the empirical formula is equal to 1 carbon atom, 2 hydrogen atoms, and 1 oxygen atom. The molar mass of the empirical formula, which is CH2O, is 30 grams per mole. My second step here is to create a ratio. The molar mass of the molecular formula, or the actual molecule, divided by the molar mass of the empirical formula. 120 grams per mole divided by 30 grams per mole. It's equal to 4. So what does that tell us? The mass of the actual molecule is 4 times the mass of the simplest formula. Since the ratio of atoms has to be preserved, 1 carbon to 2 hydrogens to 1 oxygen, this tells us that we just have 4 times the number of each of those atoms. Therefore, the molecular formula is C4H8O4. In our second example, we are going to find the molecular formula directly from the percent composition of the compound without having to first find the empirical formula. Some students find this method confusing, and so if you don't like using this method, you can always use the percent composition to find the empirical formula first, and then find the molecular formula using the method used in our first example. In this example here, we are going to assume that we're working with 1 mole of the compound. If we have 1 mole of the compound, the mass of that sample will be the molar mass by definition. My next step is to use the percent composition formula rearranged to determine the mass of each element in this 1 mole sample. So the calculation I'm doing is thinking, if I have a 58 gram sample and 82.5% of it's carbon, what's the mass of carbon in that 58 gram sample? Here I have the percent composition formula rearranged to solve for the mass of the element. The mass of carbon is going to be the mass of the compound multiplied by the percent of that element, in this case carbon, expressed as a decimal. So in this sample, 47.85 grams will be carbon, and we'll do the same thing with hydrogen. I now have the ratio of masses of the 2 elements that make up this compound. Specifically, I have the actual masses in 1 mole of this compound. My next step is to convert these masses into moles. So to turn a mass ratio in a ratio to a ratio of moles. Remember that the molar masses, whenever we're doing a mole to mass calculation, the molar masses that we're using are the molar masses for whatever particle or substance we're talking about. So here we're converting the mass of carbon, so we use the molar mass of carbon. In this calculation, we have the mass of hydrogen, so we use the molar mass of hydrogen. Now we reach the key point in this method. You'll note that my two values are very close to whole numbers. Because of the way the mole is defined, the mole ratio of atoms in 1 mole of the compound is going to be the same as the ratio of atoms in a single molecule. So in 1 mole of this compound, there are 4 moles of carbon to 10 moles of hydrogen. So in 1 molecule of this compound, there will be 4 atoms of carbon to 10 atoms of hydrogen. This is the step that often causes confusion because these steps here are very similar to the ones we used in finding the empirical formula. This method here always rests upon us using a 1 mole sample. If we use a 1 mole sample of the compound, then the ratio of moles that we'll get of the atoms within that compound will be the ratio of atoms in that molecule. So a key check here is that if you do these calculations and the mole values you get for the elements are not close to whole numbers, that tells you that you made a mistake somewhere, because these should be very close to whole numbers that you can just round and say 3.9875 is approximately 4 and 10.15 is approximately 10. So once again, to recap what we've done here. First, we assumed a 1 mole sample. Then we used the percent composition and the molar mass to determine the mass of each element in 1 mole of that compound. We took those masses and converted them to moles, and those numerical values for the moles were the numerical values for the atoms in 1 molecule.